talked about that I could have just given you yesterday and not had you graph them online, but I was hoping that by graphing this, that maybe it'll stick with you a little bit more. People get scared when they see stuff like this, but it's just the difference between like inside and outside. So if it helps you, you can think of like inside the function is like y equals x plus 2 squared, right? Or you can think of the ones on our packet there. Outside the function would be like absolute value of x and then plus 2. So inside means like in with the function part, whether it's a square or an absolute value. So when you add or subtract a number, that's going to move you left, right, up, or down. The ones that we did yesterday, we only did when the negative's on the outside. When the negative's on the outside of the function, it's going to flip it over the x-axis. But you could also put a negative on the inside of the function, and that flips it over the y-axis. But for our functions, that doesn't really do a whole lot sometimes. Like, think about if I wrote y equals parentheses negative x squared. When I square a number, am I still going to get the same answer as whether it's positive or negative? Right? Like if I plug negative 1 squared is the same as positive 1 squared. So sometimes, if it's already symmetric with the y-axis, this isn't going to change it at all. Alright? But just know, if the negative's on the inside, it's going to flip it over the y-axis, not over the x-axis. If I had a graph like this, and I flip it over the y-axis, does it look exactly the same? This side goes over here, this side goes over here. So that's what I mean by the reason I didn't give you any like that on your packet yesterday is because it looks exactly the same. Now the dilations, the rules are a little crazy, and I don't want you to stress a lot about the rules. The big thing is just know when you multiply by a number, it is going to change the shape. It's going to stretch it, it's going to shrink it. There are some shortcuts, but maybe you're just graphing XY chart. So this looks a little stressful for people when they look at this. Again, these are the two that I gave you on the homework. When you multiply on the outside of a number, that is either going to vertically stretch it or it's going to vertically shrink it, depending on whether you multiply by a number bigger than 1 or you multiply by a number between 0 and 1, like 1/2 or 1/3. And again, we graphed two of those. Horizontally, we could talk about shrinking a graph like this or stretching it out horizontally. Again, it's all about whether the number is inside or outside. So again, what are some differences here? Outside would be like 2 times the absolute value of x. Inside the function would be like the absolute value of 2x. Here's my question for you. On an absolute value graph, are these going to be any different when I actually graph them? They're going to be exactly the same. And so that's why I want to say there are definitely times it looks different, but don't stress a lot about this part. As long as you know it's a dilation, when you multiply, that's all I really want you to know right now. In pre-calculus, I'm a little meaner, and I make them learn these rules and be able to identify them. But unless you're Drew, you don't have to worry about that. So next year. So, I showed you the shortcut yesterday to graphing, but on your test, you're going to have to graph without data code. You're going to have to graph by hand. So now that we know what these transformations are, I want to show you how easily you can graph. So if I said graph y equals x plus 1 squared, you should be able to do that now. Because first of all, what type of function is this if it has x squared in it? It's a quadratic. So you got to know that. The second thing you should know is, what does it mean when I add 1 on the inside? Is it going to move it left, right, up, or down 1? And that's the part you have to kind of look at, and that's where you want to look at your packet from yesterday. You want to look at those rules I just wrote out or gave to you above here. When it's inside the function, which way does it move? Left, that amount. So I know that this is going to move left 1. Here's the great thing about graphing. You can always just make an XY chart. So if you would rather just make an XY chart here, and you know the shape of the parabola, you should be able to get there. This is where, when we were graphing before, my advice to you is always start with what makes, like, what's in the absolute value go to 0, or start with what makes this go to 0, is because that's the transformation here. So let me show you how I graph it, and then you can tell me if that makes any sense. I'm going to graph that parent function first, at least on this one, so you can see what I'm talking about. So I'm going to graph it in black as like a background. You don't have to do this if you don't want. So I'm going to graph just y equals x squared. And this is why I said when we talked about this yesterday, I think you should know what this looks like. I think you should know that x squared normally starts at 0, 0. When I go over 1, I go up 1. When I go back 1, I go up 1. When I go over 2, how many do I go up? When I go back 2, I go up 1. That is the parent function of the quadratic equation, which means when I graph that, all the other transformations are going to be based off this graph. So if you know what this graph looks like, all you got to do is know I'm moving it left 1. So the reason that I think transformations are so important is I don't have to make an XY chart to graph this. Because when I graph this, you had a magic smartboard like me. You could say, all I'm going to do is take this exact same graph, and I'm just going to move it left 1. But we don't have a smartboard to do that, right? So all I'm going to do is instead of starting at 0, 0, I'm going to take that vertex, and I'm going to move it back 1. Everything else stays the same. So starting at that new vertex, when I go over 1, I go up 1. When I go back 1, I go up 1. When I go over 2, how many am I going to go up? Go back up 4. Over 2, up 4. So I get that same shape without ever having to plug in a bunch of points. It's not wrong to plug in a bunch of points, but it takes time. There's one thing that's wrong. So I just want to encourage you to think about just sliding it over in the relationship. Because I just know those points in my head, right? If I have y equals x squared, when I plug in 0, I get 0, right? When I plug in plus or minus 1, I know that 1 squared is 1. And I know if I go over 2, I'm going to get 4. And so those are like in my head, I know those. And then I just always graph those 5 points. What about this graph? What kind of shape does this graph always look like? How does absolute value always look? V-shaped graph. What does a negative in front of that graph mean is going to happen to my graph? It's going to be pointing down. So again, if you know what the basic one looks like, the parent function, right? And so the parent function, again, I'll do it black here. You don't have to graph both every time. But the parent function starts at 0, 0, and it just goes up this line here, right? And this one goes back this way. V-shaped graph. The negative just means it flips down, which means, again, if you know the transformation, you don't have to do any work. You can just say, hey, I know it's still going to start at 0, 0, but now it's going to point down instead of point up. And I just graph it. You can always make an XY chart. Pick 0, pick 1, pick -1. It works. Alright, last one. Is this the last one? Dilations. Dilations are the one that maybe I'm going to stress that maybe you should just make an XY chart. This one's also an absolute value, which means what kind of graph should it be? A V shape. If I pick 0 for this graph, what's going to happen? I still get 0. You could pick 1 here. a number that won't give me a fraction to graph. Like 2, because 2 times 1/2 is 1. Have I got a V shape yet? Let's go backwards. Pick a negative, right? It would still give positive 1. Remember, my advice on absolute value is always start with what makes this go to 0 and pick a number on either side. In this case, I picked negative. So again, think about normally when I go over 1 in each direction. So now, because I have a 1/2 in front of it, I have to go twice as far before I can go up 1. So that's why I have to go over 2 up 1 instead of over 1 up 1. And I also have to go back 2 to go up 1. And if you want to graph 4, up 2. What's happened here is we've actually changed the shape of our graph. We've shrunk that vertically, like pushed it down. Compression. So we're going to have a test. What's going to happen next week? Same day, and there's going to be a lot of graphing on your test. And you have to do without using mode, which means you should graph these today without using mode. Tomorrow you will have a homework quiz that you do not need to use this mode. You should also be able to, because of domain range, you should be able to look at the domain range that we wrote out yesterday on our notes for those test functions and look and see are they connecting on this with the transformation. So for each of these 4 graphs, actually 6 graphs, you're going to graph it and you're going to see the domain range. You should be using it by hand. And then on the back, I gave you 2 functions using what we know about transformations now. So we write the explanation of those 2 functions on the back. Okay, so we'll check that tomorrow, we'll talk about it, we'll take the homework quiz, and then tomorrow will be our last day of new stuff for this. You don't have to graph your next if you don't want to, but if you want to do it like you did it here, so that you see it again, you just have to graph them. Okay? Stop with